Alright, so here's lesson 6.1 and 6.2 on composite, one-to-one, and inverse functions. Our objectives from this lesson is forming composite functions, finding the domain of composite functions, determining whether functions are one-to-one, obtaining the graph of inverse functions from the graph of the original function, and finding the inverse of a function that is defined by an equation. So, for composite functions, find the word much. Our first definition, given two functions f and g, the composite function denoted by f of g, which is read as f composed with g, or you just say f of g, is defined like this. So whenever you see this little circle here between two functions, or sometimes it may be a closed circle, that simply is telling you that you are going to do a composite function there. So you plug in one function into the other. So here's it in simple words, algebraically, a composite function results from plugging one function into another. So you take one function, you plug it into the other one. So let's look at some of our examples. The first one says find the following. We have f of g of x. So we're going to plug g of x into f of x. And you see f of x here is 2 times x. So when we plug in g of x into f of x, we're going to take this x out of the equation and we'll put the equation that we have for g into where the x was in f of x. So originally we would have f of x equals 2 and then x here, but because we're plugging one function into the other, we'll have f of x equals 2, and instead of plugging in the x, we'll now insert 9x squared plus 6 into its place. So there's 9x squared plus 6, and then we just simplify the function that we have left. So f of g of x is going to be 18x squared plus 12. And that is our composite function after we plug g of x into f of x. So now for b, we have g of f of x. So this time we're taking f of x and we're plugging it into g of x. So everywhere in the x equation for g, we're going to take the x out and we're going to put 2x in its place this time. So originally for g of x, we had 9x squared plus 6, but this time we're going to take the x out and we're going to put 2x in its place. So we have g and we're plugging in f of x into the g function. So we'll have 9 and then instead of x, we'll have 2x, and we're squaring that and then plus 6. So then we'll have g of f of x equals 9, and we have to square it first, so this will be 4x squared plus 6. And now we simplify by multiplying 9 times 4. That's going to equal 36x squared plus 6. And then the last one we'll do, we'll skip C and we'll just look at D. So C and D are very similar. You're just plugging the function into itself. But for D, we're plugging the G function into itself. So G of x is normally 9x squared plus 6. And we're going to take this x out of the equation and we're simply going to rewrite the equation again where this x is. So we'll have g of x, and we'll have 9, and then we're not putting the original x here. We're going to plug the whole equation where the original x was. So then we'll have 9x squared plus 6, and then we continue with the rest of the equation. So we square this, and then we add 6 to it. So now we need to simplify, and I'll go through the steps here and let you see what it looks like when it's done. And here is our final result from simplifying. So notice that if you have to square an expression, just remember that you have to multiply the expression by itself. So we squared it, we multiplied it out. Here is what it looks like once it's expanded, and then I just went ahead and combined like terms and simplified the expression from there. But this will be the final result down here. So again, you take one function and you plug it into the other to form a composite function. So now when you evaluate compositions of functions at a given value, so now we're going to be given a number. So you take the number, you plug it into the inner function, and then whatever that result is, you plug it into the one that's on the outside. So for f of g of 4, you plug 4 into g, and then you just plug the result into the f function. So here, we're going to plug 4 into the g function first. Whatever that answer is, we're going to plug that into the f function. So first we need to find g of 4, which is going to be, and we're going from our original functions that we had up here. This will be 9 times 4 squared plus 6. So if we simplify this, we'll have 9 times 16 plus 6. 9 times 16 is 90 plus 54, so that's 144 plus 6, so this will be 150. And now we need to plug the 150 into the f function. So g of 4 is 150, and now we need to find f of g of 4, which is going to be f of 150. So f of 150, remember our original f function was 2 times x, so that's going to be 2 times 150, which equals 300. Now we need to find g of f of negative 2. So this time we'll plug in negative 2 into the f function first, and then we plug that result into the g function. So first, f of negative 2 is going to be 2 times negative 2. So that will give us negative 4, and now we need to find g of negative 4. And that will be 9 times negative 4 squared plus 6, and we'll get 9 times 16 again, plus 6, so we'll end up getting 150 again this time as well. So here's how, so as you can see, it's a little bit easier when you're plugging in values into your functions because you end up getting numbers as your results. But remember, if you're plugging one function into the other function, then you should still have equations or expressions as your final results here. But when you're plugging in numbers, as you can see at the bottom, your answer should be a value for your composite function. Moving on to the next page, talking about the domains of composite functions. Remember, these are functions as well, just like any other, so they still have a domain and a range, just like any normal function would. Whenever you make a composition of polynomials by plugging one function into the other, the domain is still going to always be all real numbers because the domain of a polynomial function is already all real numbers. So it's going to still be all real numbers no matter what. So here's just an example. We plugged a linear function into a quadratic function, both of which are polynomials. And when I simplified it here, I plugged in the p of x value into f of x. I still ended up with a polynomial function as my end result. So the domain is still going to be all real numbers. However, it's different when one or both of the functions have domain restrictions. So like if you have a rational function, a square root function, an exponential or a logarithmic function, then it's going to be different. So let's see what it's going to look like. So here we have f of x is this rational function 7 over x minus 6. G of x is 9 over x. So first, A says find f of g of x. And over here we have a note. It says the new domain is going to come from whatever you're plugging in first, the inner function, and it's going to come from the simplified expression. So whatever function is going in first, you figure out what the domain of that one is going to be. And then after you simplify it, you apply the domain restrictions based on your final result. So up here for f of x, the domain is going to be x cannot be positive 6, and for g of x, our domain is going to be x cannot be 0. So now, for f of g of x, for part A, we know that for g of x, the domain is going to be x does not equal 0. So that will be a part of our domain, but then we need to find what f of g of x is and see if we have any more restrictions. So we're plugging g of x, which is 9 over x, into this function for f of x. So we're going to have 7, instead of x minus 6, we're going to have 9 over x minus 6, because we're replacing this x with 9 over x, which is the g of x function. So now, And here's a tip that we may go over some more in class if we haven't already gone over it by the time you see this video. Whenever you have a smaller fraction inside a larger fraction, you have to reduce it by multiplying the numerator and the denominator by whatever your smaller denominator is. So in this case, we have an x in the denominator of our larger fraction. So we're going to multiply the top of this function, of this fraction by x, and we'll multiply the bottom by x as well. So the x times 7 will give us 7x, and notice when we do x times 9 over x, these x's will cancel, so that will leave us with 9x. I'm sorry, that will leave us with 9, because the x's cancel, minus 6x. So now we see we have a different denominator here, so we're going to have a different domain restriction based on our new function that we have found. So now we just simply find the domain restriction for 9 minus 6x. So we set 9 minus 6x not equal to 0, and then we solve this. So we'll end up subtracting 9. So we have negative 6x does not equal negative 9, and then we divide by negative 6. We'll have x does not equal 3 over 2. So for the domain for this function, x cannot be 0 or 3 over 2. So here is our new function for part A. F of g of x is this right here. Here is our domain to match with it. And for now, we're just going to stick with looking at the domains of these functions. We'll talk about the ranges a little bit later. So let's look at part B now. So B says plug f of x into g of x this time. So we're taking this value, this function, and we're going to plug it in for the x in this equation. So this time, for g of f of x, we'll have 9 over, and instead of having our x here, we're going to plug everything we see for f of x into that. So we'll have 9 over 7 over x minus 6. So I'm going to make this fraction bar bigger so I see which part is the bigger fraction, which part is the smaller fraction. So notice now, we already know from, because we're plugging in f of x, we take that original domain, which is x cannot be 9, x cannot be 6, instead of 9. And now we need to simplify this. So remember from our previous example, you multiply by what's in the smaller, by the denominator that's in the smaller fraction. So we'll multiply the top by x minus 6, and we'll multiply this denominator by x minus 6 as well. So down here, the x minus 6's will cancel. And then in our numerator, we'll have 9 times x minus 6 over 7, and now we simply need to simplify our expression, which is going to leave us with 9x minus 54 over 7. And notice here, we don't have any more domain restrictions, so our only domain restriction comes from the original function that we plugged in, which is x does not equal 6, and here is our simplified composite function. And then if you have a constant function, like if it's f of x equals some number, it's going to be the same no matter what you plug into it. However, the domain can change depending on what is plugged into it. Because remember, the domain always comes from the inner function first and then whatever is simplified. So notice here for f of x, we have the constant function, which is 3. So this would just be the line y equals 3. G of x is a rational function here. H of x is another polynomial function. So if we plug g of x into f of x, if we take this function and try to plug it in here, we still are going to get 3 because there are no variables to substitute for this part. So we still get 3, but the domain is going to be x does not equal 0 because that comes from the g of x function. And then if we try to plug h of x, which is a polynomial function, into f of x, we still have a domain that's going to be all real numbers because the domain here is all real numbers, and the domain for our final result will still be 3, and that's going to be all real numbers as well. Now, getting into inverse functions and their properties. So, for inverse functions, these are some properties. You can read through this, but we're going to be talking about it in this section, so we'll go back to these bullet points as we discussed. So, if f is a one-to-one function with the properties shown below, complete the information for the f inverse of x. So that's how you read when you see this little -1 here. It's not an exponent, it means the inverse of f of x. So we're talking about finding the inverse of the original function. So, and because it is a one-to-one function, that's the definition that we have up here. A one-to-one function is not going to have any repeating inputs or outputs, which are x and y coordinates, and is going to pass the vertical and the horizontal line test. The only way a function can have an inverse function is if it is one-to-one in the first place, and we'll talk more about that as we go on. So, they give us some information about a function. They tell us that the domain goes from -3 to 5, where -3 is included. If we're finding the inverse function, notice our bullet point up here that says you interchange the domain in ranges. So if the domain of the original function is from -3 to 5, the range of the inverse function is going to be the -3 to 5. So the domain and the ranges will swap. Likewise, if the range of our original function is 10 to 16, then that's going to change to being the domain of our inverse function. That will be 10 to 16 here. And if you have the points on the graph that are listed here, notice we are going to be interchanging our x and y coordinates now. So if there is a point at -3 and 10, this is going to have a point at 10 and -3 because the x and y coordinates have been switched. Likewise, the 0 and 12 point is going to switch to being 12 and 0. So notice that this was a y-intercept at 0 and 12, and then it became an x-intercept at 12 and 0. So the x and y-intercepts will also switch, as will the rest of the points on the graph. And this is just a function notation of a coordinate, but this is saying when you plug 4 in for x, you get 14 for y. So on this side, when you plug 14 in for x, you will get 4 out for y. So now, moving on to determining if functions are one-to-one or not. So again, remember up here, a function is one-to-one if it doesn't have any repeating inputs or outputs, and it passes the vertical and the horizontal line test. If you remember from when we were just beginning to talk about functions, you use the vertical line test to see if it's a function. So you take a pen or pencil or something, a vertical line, and you pass it along the function. As long as it doesn't touch it in more than one place, then it is a function. So all of these are functions because they pass the vertical line test. Within the horizontal line test tells you whether or not the function is one-to-one. And notice for our first example, if you take a vertical line anywhere, it's going to touch the graph in 2 places. So this function is not one-to-one. However, our next function for number 2, if you take a vertical line, you take vertical lines and you slide it along the function, it only touches it in one place anywhere. So this one is one-to-one. And then our rational function over here, at least this example of a rational function, is also going to be one-to-one. And now we can check our ordered pairs to see if it's one-to-one. So again, no repeating inputs or outputs for our one-to-one function. So first we look at the x's. We have 3, 4, 5, and 9. So the x's check out. And for our y coordinates, we have 5, 10, 7, and 9. So none of the y coordinates repeat either. Even though these are both 9, this is a separate x and a separate y coordinate, and they don't repeat anywhere. So this function is going to be one-to-one because none of those repeat. Now for number 5, our x coordinates, we have 1, 2, 5, 8, and 10. So none of the x's repeat. And then for our y, we have 3, 4, 5, and then you see we have 3 again. So this y coordinate is repeated. So this one, even though it's a function, because none of the x's repeat, it is not one-to-one, because the y's repeat here. Alright, so now for this exercise, it's telling us to find the two indicated composite functions. So it's telling us to take g of x here and plug it into f of x first, and then we're going to take, for part B, we're going to take f of x and plug that into g of x, and we'll see what we get. So first, we're taking the g of x function here, 1 over 9 times x minus 5, and plug that in for this x. So f of g of x is going to be 9, and we're taking this x out to plug in 1 over 9 times x minus 5. So we'll get, if we distribute this 1/9 first, we'll have 9 times 1 over 9x minus 5 over 9. And then we distribute the 9, so we'll have x minus 5. And I just realized that I forgot to bring down the plus 5 here. So we'll have plus 5 added at the end of that. So we had 9, we plugged this in for x, and we had to add the 5 onto the end. So through here, we're adding the 5 onto the end. And then in our final step, these 5s will cancel, and that will simply leave us with x by itself. So now let's try part B. So this time we're plugging f of x into g of x. So we'll have 1 over 9, and we're plugging f of x in for this x. So we'll have 9x plus 5, which is what we're plugging in for the x, and then minus 5, we're bringing down that last piece. So 1 over 9 times 9x will give us x. And notice that this 5 minus 5 will cancel out from the beginning. So we're just going to be left with x again. And then C tells us to determine if they are inverse. Well, this is another part of the definition of inverse functions. If you plug one function into the other function and your answer is simply x by itself, then they are inverses. So yes, they are. So, and that's only the case if you get x by itself, not negative x, 3x, not 1/2 x, not x plus anything. It has to be x and x only. Now, the graph of a one-to-one function is given. Choose the correct graph of the inverse function f inverse of x. The diagonal line is the line y equals x. So in order to know what the graph of the inverse function is going to look like, you simply take the line y equals x, which is these diagonal lines here, and you reflect it across that line. So we're going to take this graph, which is up here like this, and we're going to reflect it over the line in that direction. And that looks like it's answer choice A, because it's been reflected across that line. So this is what it looks like when you have that reflection. And looking at one more example here, we'll take this line here, and we're going to take it and we will reflect it over this diagonal line that you see here. So if you reflect it, it doesn't look like it's going to be A, because this is a reflection across the x-axis. But it does look like it is answer choice B, because this curvy part flipped over here, and then the piece that went that way ended up on this side. So again, I'll just draw it to show you what happened. This piece was up here, and it got reflected over the line to come this way. And then this piece of the graph that was going this way also got reflected across the line, so it ended up here. And then also, you could just look for these coordinates to be swapped. So instead of it being at 4 and 1, the point should now be at 1 and 4, which it is. So that is answer choice B. So now, while we're talking about the graphs of inverse functions, I want to jump ahead to the back page of your handouts and look at this problem. It says a function has an inverse function if the graph of the function is only in the indicated quadrant. Where will its inverse lie? So if you have a function that's only in quadrant 1, so the graph of it is only somewhere up here, and it's reflected across the line y equals x. If it's somewhere up here and it's only up here, then it's going to get reflected over this line, and it will still only be in quadrant 1. However, if it's in quadrant 2 and it's somewhere up here doing something and it's reflected over this line, it's going to end up this time being in quadrant 4. Now, if we're looking at something that's in quadrant 3 and it's exclusively in quadrant 3, so for example, maybe it's down here somewhere in quadrant 3, if it's reflected over this line, that would still stay in quadrant 3. So if it's in quadrant 3, it's reflected, it will still be in quadrant 3. The coordinates still change, it moves, but it doesn't move out of quadrant 3. So this one is still in quadrant 3. And then finally, you see the illustration is still here. If you're going from quadrant 4, you see it's going to get reflected up across into quadrant 2. So it goes from quadrant 4 to quadrant 2. So now we're going back to page 5, and we're going to be graphing a function along with this inverse on the same graph here on the graph that we have. So it says also include the line y equals x on the graph. I've already gone ahead and just done the illustration for the line y equals x. It's already here for you to see. So if we graph the function 4x minus 2, that's telling us that we have a y-intercept of -2. So here's our original y-intercept, which is at -2. And for our slope, we're going to go up 4 and over 1. So we'll go up 1, 2, 3, 4, and then over 1 to match our indicated slope. And let's do another point just to be careful when we're drawing our line. So we'll go up 4 more, 1, 2, 3, 4, and then over 1 more, and then we end up with another point here. And then we're just going to draw a line going through here using my Office Depot discount card. We're going to show what our line looks like here. So our original function we've done in green, and we want to do our inverse function on the same graph. So if you notice the points that we put on our graph, we have one at 0 and -2 to start with, and then we had another one at 1 and 2, and then our final point was at 2 and 6. 2 and 6. So now to find our inverse, we are going to interchange the x and y coordinates to find the points that will be on the graph of our inverse function. So if this was at 0 and -2, we're going to have a point on the graph of our inverse function at -2 and 0. Because remember, the x and y coordinates interchange when you find your inverse functions. So then we're going to have another point on our graph. Instead of being at 1 and 2, we're going to be at 2 and 1. So here's another point at 2 and 1. And then our final point is going to be at 6 and 2. So here's 6, here's 2, here's our third point. And now we can draw our line going through these points. And here's the graph for our inverse function. So when you're working these problems out, remember, you want to start by graphing your original function and then take some points from your original function and swap the x and y coordinates out, and that will give you the points that go on your new function. So the second example says graph the function f of x equals x squared plus 2, where x is greater than 0 along with its inverse on the same graph below. So because they give us a specific restricted domain, we're only going to be able to use x coordinates that are greater than or equal to 0. So if we plug 0 in, because it can be equal to 0, we get a point at 0 and 2, because we'll have 0 squared plus 2, which is just 2. So we have 1 point. Let's do it in green again for our original function. So we have 1 point at 0 and 2. Now if we plug 1 into the function here, f of 1 is going to be 1 squared, which is 1 plus 2. So we'll have another point at 1 and 3. And then if we plug in 2, we'll have 2 squared, which is 4 plus 2. So we'll have another point at 2 and 6. And then we know it's a quadratic function. It's supposed to be a parabola. So we see our one-sided U shape developing here. And the reason why it's only one-sided is because we said x can only be greater than 0. So we only plugged in numbers that was greater than 0. If there was no restriction here, we would have been able to attach the rest of our graph here coming from the left side. So now we're going to do our inverse on the same graph. So looking at the points that we started with, we started at 0 and 2, so this time we'll be at 2 and 0. Our next point was at 1 and 3, so this time we're at 3 and 1. And then finally, our last point was at 2 and 6 here, so this point is going to be at 6 and 2. And so we have our points for our inverse function as shown. Going back to page 6, they tell us that we have a function that is one-to-one. We need to find the inverse of this function, and we're going to check our answer, which means that if you plug the function, the inverse function into itself, we should end up getting x as our solution, as our end result. So we have 2x over x plus 3, and we need to find the inverse. So to find the inverse of a function now, you switch the x and the y coordinate. So instead of having, for our original function, we have y equals 2x over x plus 3. We're going to change this y to an x, and we'll change these x's and put y's in its place. So first we need to swap it out. So we'll have x this time equals 2y over y plus 3. So now to find the inverse function, we need to solve for y after swapping the x and y. So in order to solve for y here, we see we're going to need to multiply both sides by y plus 3 to get it out of that denominator. So y plus 3 here. So we're going to have xy plus 3x equals 2y, because the y plus 3 and the y plus 3 on this side of the equation cancels. So now we need to get our y's together. So we're going to subtract xy from both sides. So minus xy. And then we'll have 3x equals 2y minus xy. Then I'll write it up so we have a little bit more space. We have 3x equals 2y minus xy. So now, if we factor the y out of this side, we'll have 3x equals y times 2 minus x. And then we can divide both sides by 2 minus x. And then we have our inverse function once we have y by itself. So these will cancel, and we'll be left with 3x over 2 minus x equals y. So here is our inverse function. So now, to check our answer, we're going to plug the original function into this function for these x's. So we're going to make a composition, we're going to make a composite function of the original function and what we suspect to be its inverse. So we'll take 3x over 2 minus x and plug it in for these x's. So we're going to take, we'll have 2 times 3x over 2 minus x all over 3x over 2 minus x plus 3. So we have our denominators, our extra denominators here that we're going to need to cancel to reduce. So we'll multiply both the top and the bottom by 2 minus x to get rid of those. So the 2 minus x's in the numerator will cancel. When we distribute 2 minus x over here, These will cancel, but we still end up multiplying 3 times 2 minus x there. So we're going to have 6x over 3x plus 3 times 2 will be 6. 3 times negative x will be negative 3x. And then we simplify, we're going to be left with 6x over 6, which cancels and leaves us with x. So, as you can see, we're left with x, which tells us that we did indeed find the inverse function, which is y equals 3x over 2 minus x. Finally, our last problem here on page 6. It says evaluate each expression using the graphs of y equals f of x and y equals g of x. So this time, instead of having an equation to plug in, we can just match the value. So remember, you need to find the value of the inner function first and then plug that into the value of the outer function. So first, for part A, we need to determine what is f of 2 based on our graph here. So f of 2 is equal to negative 1. This is the f function down here. This is the g function up here on this side. So f of 2 is negative 1. So now what we're looking for is g of negative 1. So g of negative 1 is going to be, now we're going to the g function. G of negative 1 is 4. So our final answer for g of f of 2 is 4. You find the inside value, which is negative 1, and then you evaluate that using the outside function, and that gave us 4. Part B is asking for g of f of 0. So again, we're going to the f function first to figure out what is f of 0. F of 0 is 1. So our inside function is positive 1 this time. And then we go to g. So g of 1 is going to be 5. So g of 1 is 5. So g of f of 0 equals 5. Next, for part C, we need to find g of 3. G of 3 is going to be, here's 1, here's 2, here's 3. G of 3 is 2. So g of 3 gives us 2. And then f of 2 is going to be, after 2 is negative 1. So g of, so f of g of 3 equals negative 1. Finally, we find g of 4 first. G of 4, looking at our graph, is 3. And then we need to plug the 3 into the f function. So f of 3, what we're looking for now, is 1, 2, 3. F of 3 is negative 2. So f of g of 4 is negative 2.